Okay, students, in the previous class and also video, we have discussed the application of Bernoulli's energy equation. As I have told, Bernoulli's energy equation can be used to analyze the any type of incompressible fluid flow problems. And one of the application what we have considered is to measure the discharge in the closed conduits, also in the open channel. And to measure this rate of discharge, we are using different types of devices. So those devices are venturimeter, orifice meter. These two are the devices or measuring instruments which are used to measure the rate of flow in the pipe. Similarly, we are having another device, that is the pitot tube, which can be used to measure the velocity in the open channel flows. So last class we have discussed the venturimeter and also we have derived the discharge equation, that is the actual discharge equation. So from the mathematical derivation we have got the theoretical discharge. So applying the some correction, that correction is coefficient of discharge, okay, which is actually ratio of theoretical discharge divided in actual discharge divided by theoretical discharge, or it is the ratio of actual discharge by theoretical discharge. Okay, so and also we have discussed the parts of the venturi meter. There we are having a convergent portion, a throat, and also the divergent portion. And we have taken the sections at section 1.1 before divergence, that is the actual diameter of the pipe, and also the another section at the throat. Okay, so that is about the venturimeter. Today we will discuss the orifice meter. Okay, both are same, venturimeter and orifice meter, both devices, instruments we are using to measure the rate of flow in the closed conduits. But what is the difference between orifice meter and venturimeter? In the venturimeter, as I have told, you are having a divergent part, convergent part, throat. Okay, but orifice meter is a very simple device and it is a cheapest device as compared with the venturimeter. Okay, so the orifice meter consists very simple device. It is a very simple device. It consists a plate. Okay, consists a plate. Okay, consists a plate. Okay, this is a plate like this, and we are making a hole in this plate. Okay, keeping the diameter of this hole. Okay, this is d, small d. Okay, if the diameter of pipe, okay, diameter of pipe, that is, this is in this sketch, this is the diameter of pipe. Let this is capital D, and the hole, that is a small hole, is to be taken in a plate. So keeping the diameter of this D, that is the diameter of orifice D, this is equal to 0.5 times the diameter of pipe through which we are measuring the discharge. Okay, normally this diameter, that is the diameter of venturimeter, can be kept 0.4 to 0.8. Okay, 0.4 to 0.8, you can take any value, but the standard value, that is the diameter of orifice, must be 0.5 times the diameter of pipe through which we are measuring the discharge. Okay, and it is a very simple device. You can take a plate, put a hole on that, keeping the diameter of that hole 0.5 times the diameter of pipe, and insert this plate along the cross section. of the pipe, along the cross section of the pipe. Okay, you can cut the pipe, put the this plate which is having the hole, and diameter of that hole is 0.5 times the diameter of pipe. So this is the only difference between the Venturi meter and Orifice meter. Okay, and both whenever you are going to visit fluid mechanics lab, okay, in the 5th semester as per the VTU curriculum, you will see the actual devices, that is the Venturi meter and Orifice meter. There you can also observe the difference between the Orifice meter and Venturi meter, and you are conducting the experiments, laboratory experiments on both Orifice meter and Venturi meter, using these two, how to measure the rate of flow or discharge in the pipe. Okay, so now today's class we will derive the mathematical equation for the Orifice meter. So the derivation is same as you are getting for the Venturi meter. The derivation is same as you are getting the Venturi meter. That is Q is equal to CD A1 A2 square root of 2GH divided by square root of A1 square minus A2 square, whatever equation we have derived. So you can please refer the notes. The equation is same, but the only difference between main difference between Orifice meter and Venturi meter, when we are putting a plate here and with a hole, so when the fluid passes through this hole, it is rushing very fast, means the velocity is going to reduce from the higher value to lower value very fast, because the velocity at section 1,1 is V1. At section 1,1 is V1. Okay, and when the flow or water passes through this hole, because we are reduced the cross section area of the pipe, we have reduced the cross section area of the pipe. To satisfy the continuity equation, the velocity is to be increased so that the Q remains same at section 1,1 and also at the Orifice meter. Okay, so these are the basic things. So now how to derive the equation? Okay, let us take at section 1,1, at section 1,1, at section 1,1. Okay, let P1 pressure intensity at section 1,1. Okay, then you can take, okay, let us take diameter of pipe D1. Okay, instead of taking capital D, so in the notes I have taken it is as a small d1. So please you take this diameter as d1. D1 is the diameter of pipe. Diameter of pipe. Okay. Then A1 is the cross-sectional area of the pipe. That is pi by 4 d1 square. Okay. That is the cross-sectional area of the pipe at section 1,1. Then V1, okay, is the velocity of flow at section 1,1. Okay, these are the values. That is the P1 is the pressure intensity, D1 is the diameter of pipe, A1 is the cross-sectional area of pipe at section 1,1, V1 is the velocity of flow at section 1,1. So now similarly at section 2,2. At section 2,2. Similarly at section 2,2. So let us observe the figure where we have taken the section. Okay, we have not taken the section exactly at the orifice meter. Just we have taken the section just downstream of orifice meter or this hole. Okay, this is the hole actually, or opening. Okay, as I've told. Okay, so we are supposed to have the pressure intensity value, then the diameter, cross-sectional area, velocity through this hole, because this is a hole. Okay, fluid rushes very fast. It is very, very difficult to measure the pressure intensity, velocity at this. So let us take a section just downstream side of the hole, not exactly at the hole. So this is our section 2, which is just at the downstream side of the hole, or you can call it is the orifice. Okay, so now at section 2, let P2 is the pressure intensity at section 2, at section 2. Okay, then D2 diameter of pipe, then A2 is the cross-sectional area of pipe at section 2, V2 is the velocity of flow at section 2, velocity of flow at section 2. Okay, see, whatever diameter at section 2 is not a diameter of the hole. Okay, because this is the actually diameter of the flow. Okay, so the whole diameter, let us, you can take this is as D0. Okay, area of the hole is, that is, you can take A0. It is the area of orifice meter, and this area is equal to 5/4 area of the hole, D0 square, which is normally the normal value is 0.5 times the diameter of pipe, but this value varies from 0.4 to 0.8. Okay, so these are the this is the pipe, orifice meter, and the sections. One section we are taken at the upstream side of the orifice meter, another section we have taken at the downstream side of the section. These are the various values, that is P1, D1, A1, B1 are the pressure intensities, diameter, cross-sectional area, velocity at section 1. Similarly, P2, D2, A2, V2 are the pressure intensities, diameter of pipe, cross-sectional area of pipe, velocity of pipe at section 2, and diameter of orifice meter, that is the hole which we are putting in the plate, that diameter is D0, and area at the area of the orifice meter is A0, that is 5/4 D0 square. Now for this, just you apply the Bernoulli's equation. Okay, as Bernoulli's equation is what? Bernoulli's equation at section 1, Bernoulli's equation at section 1 is Bernoulli's equation at section 1, applying Bernoulli's energy principle, that is P1 by W plus V1 square by 2G plus Z1 is equal to, okay, then the energy had at section 2 is P2 by W plus V2 square by 2G plus Z2. Okay, since the pipe is horizontal, Z1 is equal to Z2, or it is P1 by rho G, because W is equal to, W is what? It is the unit weight of water. So this W is equal to mass density of water multiplied by the acceleration due to gravity plus V1 square by 2G. This is equal to P2 divided by rho G plus V2 square by 2G, or it is P1 by rho G minus P2 by rho G. This is the, this equal to, you can take as H. This is the difference in pressure head, and this is equal to V2 square by 2G minus V1 square by 2G, or H is equal to V2 square by 2G minus V1 square by 2G. V1 square by 2G. Okay. Now H or 2GH is equal to, because 2G is common and you take it to the left hand side, this is equal to V2 square minus V1 square. V2 square minus V1 square, or 2GH plus V1 square is equal to V2 square. V2 square. So you call this as equation 1. You call this as equation 1. Okay. Now at section 2.2, at section 2.2, the actual area we have considered while calculating the velocity, this area, but the area of the orifice is A0. Okay, so we are introducing one more coefficient, that is called CC. That coefficient is called CC. CC is the coefficient of contraction. Coefficient of contraction. Okay, coefficient of contraction. And how to define this coefficient of contraction? This coefficient of contraction, it is the ratio of cross-sectional area at section 2.2 and divided by the cross-sectional area at the orifice meter. So this CC is A2 by A0. A2 by A0. Okay, because we are supposed to take the area at the orifice meter, but we are taking just at the downstream side of that. Okay, so here the area is A2, here the area is A0. We need this area instead of this area, so apply the correction. So apply the correction. How to apply the correction? The correction is to be applied in the form of a constant. That constant is called coefficient of contraction, or CC. It is the ratio of area of at section 2.2 by area at the orifice meter. Okay, so with this correction, now A2 is equal to, you have CC A0. CC A0. Now by continuity equation, that is A1 B1 is equal to A2 V2. Okay, A1 B1 is equal to A2. V2 is equal to A2 is equal to Cc A naught V2. Cc A naught V2. Okay, or V1 is equal to Cc A naught V2 divided by A1. Cc A naught divided by A1 V2, or it is, you can write like this: V1 is equal to Cc in the bracket A0 divided by A1 multiplied by V2. Substitute this value in equation 1. Substituting the value of V1 in equation 1. Okay, that is V2 square is equal to 2GH plus V1 square. V1 square is this, that is squaring this term, that is Cc square A0 by A1 square, then V2 square, or V2 is equal to square root of 2GH plus Cc square A0 A1 V2 square. Okay. So now, after further simplification, so you just or from this equation you have V2 square minus Cc square A0 A1 square V2 square, this is equal to 2GH. So V2 square is common, so taking V2 square outside the bracket, 1 minus Cc square A0 A1 square, this is equal to 2GH. Okay, so further simplification, the final equation what you are getting is Q is equal to actual discharge. Q actual is equal to CD, that is coefficient of discharge, or you can take theoretical discharge. Q theoretical is equal to A0 Cc 2GH divided by square root of 1 minus Cc square A0 A1 square, square root of 2GH, So further simplification, so already 2GH is here. So further simplifications, so please, further simplifications, you refer the notes. So the final form what we are getting, or the discharge equation for the actual discharge. So this is the theoretical discharge. So to get the actual discharge, again you apply one more correction by making the use of constant, that constant is the coefficient of discharge, which is the ratio of actual discharge multiplied by the divided by the theoretical discharge. So after simplification of that, Q actual is equal to CD A0 Cc square root of 2GH divided by square root of square root of, so this is A0, A1, 2GH square root of, this is a final step. So just you simplify mathematically, Q actually equal to CD A0, A1 square root of 2GH square root of A1 square minus A2 square. This is the final implication. So to simplify this equation, you just please refer the notes where the simplification is explained step by step. Okay, just you follow those steps, you will get this actual discharge. So this is the equation for the Orifice meter. Okay, so now we will solve one simple problem on this Orifice meter. So that is, okay, the description of the problem is going to upload. You just refer that problem. So I will read the problem. An orifice meter with orifice diameter 10 centimeter is inserted a pipe of 30 centimeter diameter. The pressure gauges fitted upstream and downstream of the orifice meter gives readings 19.02 Newton per centimeter square and 9.81 Newton per centimeter square respectively. Coefficient of discharge for the orifice meter is given as 0.6. Find the discharge of water through the pipe. Okay, the detailed description, you please refer the notes. Just I will solve this problem. Okay, so here please refer this figure. Diameter of orifice is given. That is, diameter of orifice is given. That is D naught. That is the D naught. So it is 10 centimeter or it is 0.1 meter. So A naught is equal to 5 by 4 D naught square. So this is 5 by 4.1 square. Okay, 0.1 square. So you please calculate this value. Okay. Then next is diameter of pipe. Means this is the diameter of pipe. Okay, that is D1. D1 is given 20 centimeter. 20 centimeter or it is 0.2 meter. So A1 you can calculate. That is 5 by 4.2 square. Okay, you calculate this value. Now the pressure intensities are given. Pressure intensity at section 1.1, that is P1 is equal to 19.62 Newton per centimeter square. Convert it to Newton per meter square just by multiplying 10 raised to 4. So this is the Newton per meter square at section 1.1. Similarly, P2 is the pressure at the orifice meter, that is given 9.81. 9.81 into 10 raised to 4 Newton per meter square. Now apply the discharge equation. Q actual is equal to, okay, CD value is given, that is 0.6. So whatever value you are getting, that is A0, you substitute that value here, pi by 4.1 square. A1 is 5 by 4.2 square root of 2, 9.81. Difference between these two, that is 19.62. Okay, or H you are getting okay. So CD 0.6, this, then multiplied by square root of 2GH, that is 19.62 into 10 raised to 4 minus 9.81 into 10 raised to 4 divided by square root of A1 square. A1 square is this, so substitute the A1 square minus A0 square. So you will get the discharge value. Please you calculate, you have the calculators, you calculate the values. So this is a numerical problem on the Orifice meter. So with this, just we will discuss one more measuring device, that is the potato tube. It is a very simple tube device which is used to measure the velocity of flow in the open channel, and we will discuss about the potato tube, and we will solve some more numerical problems in the last class, in the next class. That ends the model 3. So tomorrow we'll have one more video. There I am going to discuss the potato tube, how for what purpose potato tube is useful, and what is the basic principle used to measure the velocity of flow in the open channel, and we will solve some more numerical problems. Okay, thank you. You please go through all the videos, okay, which we have already uploaded. You just go through the videos and also the uploaded notes in the PDF form. Just go through the things, and if you have any doubts or difficulties, please you contact either me or Professor Sandeep Watar. Okay, thank you.